In 1968, aerospace engineer Peter Glasser published a concept for capturing unobstructed sunlight in geostationary orbit, converting it to electricity, and beaming it down to a network of receiving antennas, or rectennas, on Earth. Generating a gigawatt of continuous baseload power from orbit requires an enormous collection area. NASA's designs in the 1970s relied on monolithic, sprawling structures spanning kilometers of truss arrays. For 50 years, these theoretical models remained mathematically sound, but the massive physical scale exceeded the capacity of any existing heavy-lift rocket. With legacy launch costs hovering at $10,000 per kilogram, lofting massive payloads into geostationary orbit pushed the capital expenditure into the trillions. The math simply did not clear. Space-based solar power became the aerospace industry's ultimate dead-on-arrival trope, stranded by orbital transport economics. This history of failure raises a question. Why are dozens of independent engineering teams currently building space solar hardware? This data from the 2023 International Astronautical Congress survey maps the history of the sector. For decades, the timeline was a flat line. Between 1994 and 2017, barely any organizations existed. But look closely after 2018. The founding rate spikes vertically, tracking 52 independent commercial entities actively developing space energy technology. Today, commercial aerospace startups hold firm contracts for orbital hardware demonstrations scheduled for 2024 and 2025. The underlying variables governing space-based energy, specifically launch cost and payload mass, have shifted enough to invalidate the old models of failure. The primary bottleneck has always been payload constraints. A gigawatt-scale orbital power plant requires transporting roughly 100,000 kilograms of hardware 35,000 kilometers above the Earth's surface. This diagram shows the legacy transport equation. Multiplying 100,000 kilograms by traditional expendable rocket costs of $10,000 per kilogram outputs a transport cost of $1 billion, just to place a tiny fraction of the required mass into space. That equation is currently being dismantled by super-heavy, fully reusable launch architectures designed to prioritize extreme payload volumes over bespoke single-use reliability. Vehicles like SpaceX's Starship are structurally scaling the launch market. Instead of expending a multi-million-dollar booster to deliver a few tons, these architectures are engineered to deliver 100 to 150 tons to orbit per flight, designed for rapid reuse multiple times a day. Run that legacy equation again with projected super-heavy launch costs. When the transport variable drops from $10,000 to $100 per kilogram, the total deployment cost plummets exponentially. Launch mass is transitioning from an insurmountable financial barrier to a standard bulk rate utility expense. Cheaper rockets solve the transport barrier, but the payload itself requires a mass reduction. Traditional, rigid, multi-junction gallium arsenide solar cells, the standard for decades, are far too heavy to scale effectively into gigawatt arrays. The solution comes from recent commercial manufacturing breakthroughs in thin-film, self-curing silicon and printed perovskite solar cells. Aerospace engineers evaluate hardware using specific power, the metric of watts generated per kilogram of mass. Thin-film cells increase this ratio by stripping away heavy glass and rigid backing materials. By minimizing mass and volume, operators can pack more gigawatt generation capacity into a single rocket fairing, maximizing the energy yield of every launch. Once in orbit, kilometer-scale power plants cannot be deployed as single pre-built structures. They also cannot rely on complex unfolding mechanisms, which carry a high risk of mechanical failure. The arrays must be assembled on site. Upcoming demonstration missions, like NASA's OSAM-1, are currently proving out the mechanics of autonomous in-space robotic construction. Instead of launching completed satellites, rockets will deliver standardized, repeating components. Autonomous robotic arms will snap these modular segments together directly in microgravity. Space solar architecture is moving away from giant, fragile deployments and toward high-volume, automated manufacturing in orbit. Capturing the energy is only the first step. The defining technological hurdle is transmitting concentrated power across the vacuum of space and through Earth's atmosphere without catastrophic thermal loss. This graphic breaks down the competing transmission modalities. Microwaves easily penetrate heavy cloud cover, making RF beaming necessary for continuous terrestrial baseload power. Lasers offer tighter beam divergence, allowing smaller receivers, but optical beams suffer from severe atmospheric attenuation and require clear weather. The major enabler for both methods is the rapid maturation of commercial phased array technology. Instead of physically moving giant mechanical antennas, operators can electronically steer power beams with pinpoint precision. This level of control makes extreme megastructures feasible. Concepts like the lunar ring propose a continuous solar belt around the moon's equator, utilizing phased arrays to beam microwave energy constantly back to Earth. The transmission physics directly dictate the business model. RF architecture targets massive terrestrial grids, while laser architecture caters to niche, highly localized power delivery. There is a severe capital constraint to consider. Private markets will not fund a 20-year research and development phase if there is no intermediate revenue. To cross this financial barrier, the industry is pivoting. Startups are utilizing their core power beaming technology to service smaller, high-value stepping stone markets first. The clearest near-term commercial application for wireless power transfer is the lunar surface. For hardware operating in permanently shadowed craters, a beamed optical power link from a nearby solar hub provides a localized, mission-critical utility grid. Beaming power allows lunar rovers and landers to survive the freezing 14-day lunar night without having to carry heavy, politically sensitive nuclear heating systems on board. Similar stepping stones exist in low Earth orbit. Space-to-space networks propose beaming energy from a central hub directly to commercial satellites, eliminating their battery-draining eclipse periods in Earth's shadow. Terrestrial military applications are also driving immediate R&D. DARPA's POWER program is currently funding the development of airborne optical relays, designed to transmit energy continuously to drones so they never have to land. Space-based solar power is no longer an all-or-nothing gamble on a gigawatt terrestrial plant. It is an iterative roadmap, financed by high-margin orbital and lunar utility contracts. We can map exactly who is building this stepping stone infrastructure by looking back at the 2023 IAC survey. This global map tracks the 52 commercial entities surveyed, revealing clusters concentrated primarily in the US, UK, and Europe. Filtering out concept or dormant pins leaves the illuminated active market built-in actionable hardware. While many startups are operating on seed funding, key players like Virtus Solis, Emrod, and major defense contractors like Northrop Grumman have secured millions in private and government capital to deploy their architectures. The physics are now leaving the lab. Successful terrestrial demonstrations of both RF and laser power beaming have recently been completed across distances of up to 1 kilometer. The sector has systematically transitioned from academic white papers to competitive, capitalized hardware prototyping. The barrier to space-based solar power is no longer a question of theoretical physics, nor is it a question of impossible baseline economics. Deploying these systems is now a massive but highly pragmatic systems engineering challenge. The true test of this industry will not be the sudden deployment of a massive orbital array powering a major city overnight. Validation will arrive incrementally. The first successful sub-megawatt orbital power transfers are expected to establish proof of concept by the end of this decade. Cheap, reusable launch profiles, ultra-lightweight photovoltaics, and commercial phased arrays has broken the 50-year deadlock. At $20 per kilogram, the manufacturing of orbital arrays is now a standard industrial project.